Welcome to Excel Business Statistical Analysis video number 50. And in this video, we got to talk about one of the most amazing business math tools, simple linear regression. And we'll cover a lot of topics in this video, but it'll be one video that explains it all. Now here are the 8 amazing topics we're going to cover in this video. And we'll start off with a data set. And just as we did back in Chapter 2, we'll plot using an XY scatter chart to see if there's a relationship. As X increases, does Y increase? Or as X increases, does Y decrease? Or is there no relationship at all? Then, in this chapter, we'll calculate a bunch of measures. We'll have a measure called correlation, which will tell us the strength and direction of the relationship. And it will be a number from -1 to 1, where minus will indicate a negative or indirect relationship, and positive, a positive or direct relationship. Then we'll calculate the slope and the y-intercept, and that will allow us to create our estimated simple linear regression line. That line will help us make predictions. We'll also have to calculate, very importantly, R squared. That's a goodness of fit measure that tells us, hey, our estimated equation, how much better is it at making predictions than the Ybar model? Then we'll calculate the standard deviation between the actual data points and the predicted points on the estimated equation line. And we'll finally test the reasonableness of the relationship between X and Y. Now, these two XY scatter plots look a lot different than how we created them back in Chapter 2. But we're going to add some extra lines to help visualize the deviations and the residuals, because the visualization will help us understand all of the math we have to do. Not only that, but we're going to do all the calculations longhand, just like when we studied standard deviation, because the math behind the statistics will help reveal the meaning of the statistics. All right, now we want to go over to the sheet X adds and Y sales. Now here's the sheet where we're going to make all of our awesome math calculations for our measures. But before we do that, I want to scroll down, zoom in, and here we have a business data set. And the company collected by week the number of dollars spent on ad and weekly sales. And we want to see if there's a relationship. Hopefully, the more ad dollars we spend, the higher weekly sales will be. Now, the X variable is the independent variable or the predictor variable. And the Y variable is the dependent or predicted variable. Later, when we have our equation to make predictions, we'll put in an X, and the equation will predict a Y. However, all of the techniques we use to create the equation and all of the other measures, none of these things prove causation. We're just going to use the correlation to help make predictions. Now, the first task is to make an XY scatter chart to visually see if there's a relationship. Let's highlight the field names, Control-Shift-Down arrow. And instead of going to Insert, Charts, XY, well, we could do that. And we did do it back in Chapter 2 when we manually built the chart. But in Excel, the Home Ribbon tab, Analysis Group, this Analyze Data, it actually uses AI to look at the data, detect patterns, and then it suggests reports and visuals. Now, it doesn't always make smart suggestions, but when it's given XY data, it always, at least every time I've ever seen it, gives you virtually a perfect chart. So I'm going to click Analyze Data, and sure enough, right at the top, there's our XY scatter. When we click Insert Chart, it gives us an awesome chart. It has a title that even says X and Y appear highly correlated. It correctly lists the labels for the Y and X variable. For both axes, numbers are listed in a less cluttered way by showing the numbers in thousands. It lists all the markers, and look at that. It even shows the line that will be created by the equation. So with one click, we have a complete chart. Now, what's the relationship? It looks like as add dollars spent per week, the X variable, as it increases, the Y weekly sales increases. So it looks like there's a positive or direct relationship. Now down here, this is a chart we'll make a little bit later. BMX race bike weight and the price of the bike. So here, this looks like an indirect or negative relationship. As the weight of the bike increases, the price decreases. Now these charts provide visual evidence of the relationship, positive or negative. But now we'd like to calculate a measure that'll tell us what type of relationship it is. Now I actually want to cut this chart because we're down at row 230, and I want to paste it above where our formulas are going to be. Control X, and then we scroll up. F204, Control V. Now up here, we have the same exact data set, but notice rows 12 to 198 are hidden. Now, I hid all those rows so that we can make our calculations more easily. But all the data points are still there. And when we make our calculations, it'll make it from all the data points. Now, before we can calculate our measures, I want to plot an Xbar line and a Ybar line. The Ybar line will make it easy to see the Y deviations, either above or below. And the Xbar line will allow us to see the X deviations, either below or above. Now, how do we determine a line? Well, all we need is 2 points. So if we want a line, and up here I calculated the mean for all the Y values and the mean for all the X values. But if we want a line that shows us Y bar at every X value, well, we could take X equal to whatever the min value is and plot it right at 370,000, and then take the max X and plot it right at 370,000 Y. We'd have our 2 points. Then we could create a line. Now up here, I already calculated the min for all the X's, the max, and then listed Y bar twice. X and Y, 2 points. That will determine a line. Now we're also going to need an X bar line. So we want a vertical line right down the middle. So we'll have as data points X bar listed twice and the min and max from the Y values. And we also want to plot a single marker at the X bar, Y bar point. All right, come down to our chart. Let's select the grid lines. Not the full inside chart, but just the grid lines, and hit the delete key. Do it for the vertical ones also. Now to add a data series to our chart, we can either go to Chart Design, Select Data, or right-click, Select Data. Now here's the Select Data Source dialog box, and legend entries for the series. Series always means numbers. We want to click Add. For series name, our first one is going to be the Y bar line. And watch this. I'm going to hit Tab, select the 2 X's. But when I hit Tab, that little array will cause trouble unless you use the delete key to delete it. Then we select our Y's, click OK, Add. This will be Xbar tab, the 2 X values tab, delete the 2 Y values. Click OK. Add, series name, XY mean plot tab. There's the single X tab. Delete the single Y. Click OK. When we click OK, now we have some markers, but we need a line. That means we need to change the chart type. So somewhere in the chart, right-click, and then point to Change Chart Type. Now, the nice thing about this dialog box is down here. Actually, let me pull this up. Pull the right corner down. Is that it shows us a list of all the series. For Y bar, I'm going to change the chart type to just a line. We can see the preview. Same for X bar. That's exactly what we want. And for X mean plot, we want that as a scatter marker. So click OK. And now let's format. We can select the line, Control 1. It didn't come up right, but we know it's the paint bucket. For the line, I want a solid line. Let's make this dark blue. The Y bar line, solid. I'll make this black. Now the X bar marker is hard to select. So we'll go up to the Format Chart tab, current selection, and we'll select XY mean plot. We can see it selected, paint bucket. This is a marker, so I'm going to select marker, marker options. Built in, let's change it to a triangle, increase the size. For fill, I want solid fill, red, and that is looking good. Now with that marker for our X bar and Y bar selected, we come up to the green plus, and I definitely want data labels. Click the arrow, more options. Wow, it didn't come up right again, but I know it's series. Sometimes you have to just click around to find what you want. Label options, Y value, leader line, X value, and series name. Notice we named the series smartly, so it will help us in our chart. There it is. Click and drag. We can resize it. And so now we have a chart. If we zoom in, there's our chart with all the markers, the predicted line, X bar, Y bar, and a marker for that X and Y mean. Notice that that marker is right in the intersection of X bar and Y bar, and it's also on the eventual predicted line. Now, the reason we did this is because in order to calculate a measure that determines whether it's positive or negative, we're going to calculate something called covariance. And here's how it's going to work. And it's actually quite clever. Notice anything above the Y bar line is a positive Y deviation. And anything above the X bar line would be a positive X deviation. Now, what would happen if we took the deviation for Y bar, which is positive, and the deviation for X bar, which is positive, and multiplied them? We'd have a positive times a positive, which would give us some big positive number. But notice all the markers in this quadrant will have a positive X deviation for every single point and a positive Y deviation for every single point. Now, let's go down to this quadrant here. How about this value right here? The X value right there is way below the X bar value. So this deviation would be negative. For the Y deviation, well, there's the Y bar. There's the Y marker. So this is also a negative deviation. If we take negative deviation for X, negative deviation for Y, both negative numbers, and multiply them, well, guess what? We're going to get some big, huge positive number. Anything in this quadrant, for example, that marker, it's below the X bar but above the Y bar. Negative times a positive would give us a negative number. Down here, negative Y deviation, positive X deviation. So multiplying a negative times a positive, we're going to get some big negative number. So that's the trick. If we multiply all of the Y deviations times all the X deviations, all the values in quadrant 1 and quadrant 3 will be big and positive. All the values in quadrant 2 and 4 will be big and negative. So when there's a preponderance of markers in quadrant 1 and 3, when you add them all up to get a total, you're going to have some big, huge positive number. And that will indicate that the relationship is positive or direct. Notice in this case, we have some negatives in quadrant 2 and 4, but there's certainly not very many of these. Lots of them here and here. Now, if we look at our bike example, it looks like quadrant 2 and quadrant 4 has the higher preponderance of markers. So that means when we add them all up, we're going to have more negatives, and we'll get some big negative number. And that's how we'll know. When we get, for covariance, some big negative number, we'll say that the relationship is negative or indirect. For covariance, if we get a big positive number, we'll say it's direct or positive. Now let's make these calculations. We're going to zoom in a bit. Now on the formula sheet, these are all the different formulas we're going to use in this chapter. They're also in the PowerPoint slides and in the textbook. This is the one we're doing right now, sample covariance. Over on the sheet, add and sales. Here's all the X and Y values. And notice there's lots of hidden rows. We need to calculate deviations for both X and Y and then multiply them. So in this column, equals, we're going to highlight the whole column of X values. And notice it looks like I only highlighted 3 cells, but sure enough, it got the full range, D10 to D99. Then from those particular x values, we'll subtract Xbar and enter. Those are all the x deviations. And from our study of standard deviation, we know if we Alt equals to add up all the deviations, we're always going to get 0. Now we do deviations here. Later we're going to do errors, and they always add up to 0. That's why we end up having to use the square root. So when we add them, we get something different than 0. Y deviations, all the y values minus y bar. Enter. Alt equals, and the sum of the deviations equals 0. Now we multiply equals the full column of x deviations times the full column of y deviations. And when I hit enter, it spills the results. Come to the bottom to get our numerator, Alt equals, and enter. That number is the numerator for sample covariance. Now we can come over here and calculate sample covariance. There's the numerator divided by, in parentheses, I've already calculated n. That's how many records we have. So n minus 1, close parentheses. And when I hit enter, that's our sample covariance. Now we have a numerical measure, a big positive number that indicates that we have a positive or direct relationship between ad dollars spent per week, X, and weekly sales, Y. Now, I wasn't supposed to have this here. Now, we did it longhand, but later we don't have to do it longhand. We can just use the built-in function covariance. Now, P is for population, S is for sample, so we're going to use sample. Now, there are many different linear regression functions, and they're all going to require that we put in y's and x's. Now, the strange thing is a few of them say array 1, array 2. That means you can put them in any order. But most of them, as we will see, will insist that we put the y values in first. So even though this doesn't require that, my rule is I'm always putting the y values in first. Then I'm never going to make a mistake. Comma, array 2, those are the x values. And of course, when I hit enter, I get exactly the same number, a really big positive number. So that's covariance. And by the way, see those little red triangles? If you hover your cursor, that gives you a short description of the measure and the formula. So for each one of these, there's a little pop-up. Now, if we hover our cursor here, sample covariance will measure the linear relationship between two quantitative variables. But it does have a problem with units. Now, we're not going to have a problem here, but imagine if we were measuring something in feet, we could get some covariance. But if we switch from feet to inches, then the covariance would be much bigger, even though the linear association or relationship would be exactly the same. So this is really a blunt way to calculate the strength of the relationship. What we really want to calculate is coefficient of correlation. And conveniently, it will calculate a number between -1 and 1. And it will measure not just the direction, but the strength and the direction of the linear relationship between 1x and 1y. The closer to 1, the stronger the positive relationship. Closer to -1, the stronger the negative relationship. And the way we're going to accomplish this is we're going to take sample covariance and divide it by standard deviation to get the measure in units of standard deviation. But notice, since we multiplied in the numerator deviation for x times deviation for y, when we want to convert it to units of standard deviation, in the denominator, we're going to take standard deviation of x times standard deviation of y. Well, of course, that means we're going to need to calculate sample standard deviation for x and y. If you hover your cursor, there's the formula we learned back in Chapter 3. Notice we calculate deviation squared, then sum, then divide by n minus 1, and take the square root. Well, guess what? The sum of the deviation squared divided by n minus 1, we're going to use that in multiple other calculations in this chapter. For example, we'll use the sum of the y deviation squared to calculate something called sum of squares total. And we'll use this one when we calculate our slope. So equals, there's the x deviations, caret 2 to square, and enter. Now, I don't know why that formatting isn't working, so I'm going to right-click that cell, Format Painter, and click. Y deviations, caret 2, and enter. Now we'll add these up. Alt equals and enter. Alt equals and enter. Now we'll come up here. We're calculating standard deviation for x. So the square root x deviation squared divided by, in parentheses, n minus 1, close, close, tab. There's the standard deviation for x, equals the square root of sum of y deviation squared divided by n minus 1. Close, close. And now we have both of our standard deviations. Now we can come down and calculate coefficient of correlation. We're going to take sample covariance and divide it by, well, we need to multiply these, and we could do it in parentheses with a multiplication operator, but I'm going to use the product function. We have our two standard deviations right next to each other, so that's an easy way to do it. Close parentheses, and when I enter, there's our coefficient of correlation. That means as x increases, y increases with a strong positive relationship. Because this number is positive, it tells us that we have a positive or direct relationship. Because it's close to 1, we know that it's a strong linear relationship between x and y. Now, there are two different built-in functions that calculate exactly the same number. The function CORREL will work, but there's a second function that's named after the statistician that invented this, Pearson. So I'm going to use that one. Notice array 1, array 2, I'm always going to put in y first, comma, and then x. And when I hit enter, I get exactly the same coefficient of correlation. Now, with this measure that tells us that we have a strong positive relationship, we actually want to create the equation that defines this line so that we can help ourselves make business decisions. Because it looks like as ad dollars increase, weekly sales increase. So we want to be able to just pick any particular x and then estimate what the y should be. Now, our next calculation we need to make is the slope of the estimated equation and line, and then y-intercept. Now, I actually want to jump over to some PowerPoints and talk about the equation we're going to create. We're on slide number 18. Now, in algebra, you may have seen y equals mx plus b. Y, that's the value we're trying to predict. X, that's the value we throw into this equation, the independent variable that will predict the dependent or predicted variable. The m is the slope. The b is the y-intercept. Well, that's algebra. Here in statistics, we have two different equations, one for our population parameters and one for our sample statistics. Yes, we usually aren't going to know the actual population y-intercept or the population slope. So we're going to have to use methods to calculate the sample statistics for slope and for intercept. This will be called y hat. And I will write it like this, or actually use the symbol. Y hat equals slope times x plus y-intercept. Now, slope, whichever variable you use, the meaning of the slope is going to be for every 1 unit of x, how much does y change? In a positive relationship, y will go up. In a negative relationship, y will go down. And the intercept, whichever variable you use, it simply is going to tell us at what point does the line cross the y-axis. Or what is y when x equals 0? And of course, this equation, any one of these equations, describes a straight line. Now let's go to our next slide, because guess what? We're not always going to have our population parameter. So the simple linear regression model, y equals slope times x plus intercept plus an error value. Now these are called beta sub 1, beta sub 0, and this is epsilon. Now, this error is going to come from the fact that we're creating an equation or a straight line. And I'm going to go to the next slide. And guess what? All of the original sample data points are not on the straight line. This straight line comes from this equation. We're going to create this equation for making prediction. There's the slope, there's the x, there's the y-intercept. That equation describes that line. And because all of the sample point markers above and below are not exactly on the line, we have some error. Now, if we're going to use this model, we have to make some assumptions about this error. So again, there's some sample points that are above and below. And I want you to think about this for a second. Here's a marker above. That's the actual value from our sample. But look at where the prediction's going to be. The prediction's going to be way down here. So in this particular instance, the actual predicted value is less than the particular value from the sample. The model or the equation underpredicts. Down here, it's the opposite. The model overpredicts. So because we don't want our equation to overpredict or underpredict too much, we want to look at the assumptions necessary for such a model that will not over or underpredict too much. Now, notice this has x and y. When I go to the next slide, we're going to look at these assumptions necessary. I'm going to tip this on its side. So next slide. Now notice I've tilted this, but the x, that's weekly ad expense, and y, predicted weekly sales, they're still there. I've just tilted it on the side. And these bell-shaped distributions are our assumptions about how the error should be distributed. Now, here's the line. There's the equation. And notice no error term, because right on the line, the expected value of epsilon should be 0. That's our first assumption. And all that means is if this is a probability distribution for the possible error values above or below, as we go higher and higher above the line or below the line, the probability gets smaller and smaller that we could get one of those errors. And right in the middle, that's where the frequency is highest, the probability is highest. We're hoping to get errors right at 0 or close. So in order for this line to not over and under predict too much, we really need most of the errors to be right near the middle. So number one, the expected value of epsilon or error is going to be a 0. If that's true, we can treat the slope and the y-intercept as a constant and not include our error term. Assumption number two, we have a bell-shaped distribution. Hopefully, most of the errors are right near the middle. Now, the third assumption is that that error, the variation or the standard deviation, will be constant across all of the x's on our line. Now, we'll actually be able to test this later using what's called a residual plot. We also want to notice that expected value of y given x, that's actually for population values. So if you imagine that scatter plot we just saw, if there was some values for the y up above and below the line, if we took the mean of all those, then the expected value of y for the population given a particular x would be exactly on the line. Now, if that's true for this equation, if we go to our next slide, then we can see we don't have to show the distribution of errors because expected value of epsilon, the error is going to be 0. So there is what is called the simple linear regression equation without the error value. Now go back to slide number 19. When we use the word model, that's the parameters and the error. If we go to slide number 22, simple linear regression equation, population parameters without the error value. Now, of course, most of the time we are not going to have our population parameter, slope, and y-intercept. So we're going to have to figure out formulas to calculate both of those to create our sample statistics for slope and y-intercept. If we go to slide number 24, we can see estimated simple linear regression equation. So this will be called y hat. I'm going to sometimes do it as y sub hat or use the actual symbol. Sample statistic slope times x plus sample statistic y-intercept. Now this value will predict two different things. If we want to estimate the population parameter, then y hat will be the point estimator of expected population value of y given a particular x. That'll be the mean of all the y values for a particular x in the population. But most of the time, we're going to be using y hat to make predictions. Y hat can predict an individual y value for a particular business situation. So we're going to use y hat for our weekly ad expenses and weekly sales. We'll simply throw in an x, say 43,000 for our weekly ad expense, and the y hat will tell us what our predicted weekly sales will be. Now we need our formula for calculating slope and y-intercept. Let's go to slide 27. For slope b sub 1, we have numerator and denominator. And look at this. This is the same deviation of x times deviation of y we did for covariance and correlation. And then in denominator, we're going to take the sum of the x deviations squared. Once we get our b, we simply plug it into this equation, y bar minus slope times x bar. We will then have our sample statistic for y-intercept and for our slope. Here are the variables. Here are some alternatives you may see. We're going to use this formula, but you may see this as a formula for slope or this one. Now let's talk about how this formula was created. I'm going to go back to slide 26. The least squares method was used to derive the formula for slope. Now it minimizes this component right here and then uses differential calculus to get to this. Now knowing how to derive this formula is not required for this class. But just in case you're curious, I hand wrote the deductive proof. And it's in the links below the video or at our class website. And there's two of them. There's a big long one. This one goes on for 7 pages using differential calculus to prove those formulas. And then there's a shorter abbreviated one. All right, now we want to jump over to Excel and calculate the slope and y-intercept for our data set. All right, we're going to calculate slope, and sure enough, there is the formula. In the numerator, it's the product of the deviations. And in the denominator, it's the sum of the x deviations squared. So here we go. We already made these calculations equal. There's the sum of the product of both sets of deviations divided by, and here's the sum of the x deviations squared. And when I hit enter, I get a slope of 8.24. Now, this slope means that as a predicting model, for every $1 spent on ads, the estimated equation predicts that sales would increase by $8.24. Now, there's a built-in function for slope, and they named it smartly, slope. And notice this is the first linear regression formula we've seen where explicitly the y is listed first. But we already know that. That's going to be our habit. So we got our y's, comma, there's our x values. And when I hit enter, I get exactly the same thing. For every $1 of ad, sales are predicted to go up by $8.24. Now, conveniently, once we know slope, and we also have a marker on the estimated line, notice that x bar and y bar are both on the line. From our equation, if we subtract slope times x from each side, we get this. And since we know slope and 2 points on the line, x bar and y bar, we plug those in to solve for intercept. So that's what we're going to do. Equals y bar minus slope times our x value, which is x bar. And when I hit enter, we have a y-intercept of 36,857. That means if we extended the estimated equation all the way to the y-axis, that is where x equals to 0, it would cross right at about 36,000. Now, we would never make a prediction out here because we want to keep our x values that we put into the estimated equations to make predictions within the experimental range, whatever the min value and the max value is from the original x values. So at x equal to 0, the estimated equation predicts that the sales will be about 36,000. Because 0 is not in the experimental range, an extrapolation like this provides an unreliable estimate. Now, there is a built-in function, and it's smartly named intercept. There's the y's, comma, there's the x's. And when I hit enter, I get the same y-intercept. Now, I want to actually create with the formula the y-hat equation. And this is not required. You don't have to do this. You could type it out. But we will see one advantage. Equals, and I need text, so I double quote, y-hat equals, with the right spaces, in double quotes, and I need to join it to the slope. But this slope has a lot of messy decimals, and intercept also. Now, I could use the round function, but there's an amazing function called fixed. And all it does is it will format this as if it had a number formatting. That means when we get big numbers like this, it'll put the comma. And the default is to show it with only 2 decimals. So there's the number. I don't need to put any of these in because we're going to use the defaults. Just for a second, let's Control Enter. And you can see it's displaying with just 2 decimals, F2. And we're going to join it to some more text in double quotes times x space. We need a plus symbol, space, end double quotes. And let's fix this one also. Close parentheses and enter. There is our formula. Now, the advantage to creating a formula, of course, is if you change the source input. I'm just going to change one of these y's to 5, and then let's see if it updates. Bam! Everything updates. Now, let's Control Z to undo that. Now, I do want to figure out the experimental range parameter, so I'm going to equals min of all the x's. That'll be our lower bound. So about 14,500 equals max of the x's. So about 64,700. Now, I guess in summary, the sample data provides evidence that there's a direct relationship between ad dollars per week and weekly sales over the experimental range from about 14,000 to 64,000. And then we have our equation. Now, let's make a prediction. We're going to say, hey, I want to know what the weekly sales are if we spend $50,000 in ads for the week. Equals slope times x plus y-intercept. And when I hit enter, it looks like about 448,000 or 449,000. That's our predicted value. Now I want to come over to the chart and see if we can select our estimated equation line, then use Control 1 to open the Format Trend task pane, and come down and check Display Equation on Chart and R squared. Let's close this. Now, I actually already pre-formatted this. If it's not red and you wanted a different color, I just used home font. But there's our equation now on the chart, on the visualization. But R squared is what we want to calculate next. And R squared tells you the goodness of fit of the estimated line in the equation to our data points. Or more specifically, it tells us how much better using this estimated line to make predictions is than a Y-bar model. Now we're going to jump back over to PowerPoint. Now we want to take a closer look at R squared, which is a measure of the goodness of fit of the estimated equation line to the actual data points. Now let's think about this line. What would it mean if we had a perfect equation that predicted exactly like the original sample points? Go to our next slide. It would look like this. That means we would have our line, and all of the original sample points would be exactly on the line. But that's not what we have. Here's what we have. Here's our estimated regression line. And there's all of the original sample data points. They're not on the line. You can think of the distance between each one of the original markers or the original sample points in the line as a bit of an error when we use this model. Now, the distance between a particular value and the estimated value we would get at that x value is called a residual. Now, if we go to our next slide, we can see a picture of what the residuals look like. Here's our original sample data points, and in each one of these sample data points is a y value. Well, guess what? This equation is predicting y hat, which is a y value. If we took the predicted value and the particular value from our sample and compared them, the distance between those would be our residuals. And we'll actually say, hey, the original y value, and we'll subtract the predicted value. Now, sometimes the actual predicted value will be underneath, which means the equation is under predicting. Other times, it will overpredict. Here's our estimation right there. There was the original y sample point from our sample data. It's way below. Now, calculating the residuals is not hard. We go to our next slide. Here's our original sample x values, our original sample y values. And we already calculated the slope and the intercept. So guess what? We're going to take our y hat, but each one of the x's will be from the original data set. And if we calculate that down, we have y hats. That means we have an exact predicted value at the same x as the original sample y value. Then we simply subtract. I'm going to say particular y minus the predicted. And this is called the residual. And when we make all of those calculations, we get the distance, that red line, for each one of our original x values. Now, check this out. If we were going to add these up, because we want to analyze the error in using our model as compared to the original sample points, if we add these up, we get 0, just like with our deviations. Now, since we want to analyze these, we will get around that the same way we did when we did standard deviation and deviations earlier. We will square the values and then add them up. And that'll be called the sum of the squares of the errors. Now, before we go and calculate that, I want to think about our model here. This is the y hat model compared to a Ybar model. What's a Ybar? Now, we saw how to plot this, but think about this. If a manager in a business didn't bother to go out and see if there was a relationship between weekly ad expense and weekly sales to try and build this model here to predict, right, as weekly ad expense increases, it looks like weekly sales increase. If the manager didn't do that, they might be stuck with just using Ybar at every single possible x. That means no matter what the weekly ad expense was, they would just be using Ybar. Now, we want to think about what would happen if we only used Ybar. Well, there's the particular value, right? They're all over here. Look at the distance there. So the error in using Ybar as our model would be huge. Now look at our y hat model. The distance between using the actual predicted value and the particular value is much smaller. That is going to be the essence of calculating r squared, the goodness of fit. So a lot of errors when making predictions with our Ybar model. These are called deviations. Much less error when we're using our estimated equation. And these errors are called residuals. Next slide, our calculation, as we mentioned, is going to be called r squared, also known as coefficient of determination. And it will measure the goodness of the fit of our estimated regression line to the actual sample data points. Now, before we go and calculate in review, here's what a perfect model would look like. All the points on the line. Here's our residuals. That's the error in using our estimated regression equation. Here's the total error that we would have if we use Ybar. You can see that's much bigger than the error we would get if we used our regression equation. Now, there's actually two parts in this error. If we go to our next slide, here's the total amount. That's the total error. But this total error, you see that line kind of splits it in two? there's two parts. The first part is the actual error in us using the estimated equation to make a prediction. But guess what? This bottom part is the extra benefit we get in using our estimated line over the Y-bar line. Now, let's see how to calculate both of these errors. Total error, as it will be called, is always going to be the particular value minus the Y-bar. The actual residual, particular value minus the predicted. You can see particular value minus y hat. And the bottom part is going to be, hey, this is the part that's explained by using our regression equation. That's going to be the predicted value minus the y-bar. So y hat minus y-bar. Now, there's some synonyms for this error, right? Residual, error, or the unexplained part of total error when we use our regression equation. This part here is the explained part. Again, it's like the benefit of using this equation over a y-bar equation. It's also called the regression amount. Now, here's what we'd like to do. I'd like to calculate every single blue line for every single point and add it up, and then do the same for the residuals and add it up. And then we can compare those two parts to the total and get what percentage is explained by using the equation and which part is not explained. But we already know what the problem is. If we add up all the residuals, we get 0. Guess what? If we add up all these, we're going to get 0 too. So if we look at our next slide, and we'll go do this in just a second. Here's the total. And we already know this one. This is from doing standard deviation, a particular value minus the mean. Do it for every single one. You're always going to get a total of 0 for all the deviations. Here's our residual. We already saw that that adds up to 0, but also the explained part or the regression part. If we take our predicted value minus y-bar, do it for every single original x, get a total of 0. Hey, but that's no problem. We know what to do. We can square all these and then add them up just like we did for standard deviation. Next slide. That's exactly what we do. Just like for standard deviation, particular value minus the mean, square it, add them up, except for now in our analysis of our regression equation, this will be called sum of the squares total. That's the total error, in essence, of using y-bar. And we have one, two part. The regression part, predicted value minus y-bar squared, do it for each individual x and add them up. That's called sum of the squares of regression. Our residual squared will take particular y minus the predicted, square it, do it for each individual x, add it up. That'll be sum of the squares of error. Now, there's an important relationship between these. Remember, if we go back a slide here, two parts make the whole. If you add the individual error to the individual regression, when you add them up, you get exactly the total. If we go back to slide 44, that's the same relationship here. If you add sum of the squares of regression to sum of the squares error, you're going to get sum of the square total. So our next slide defines each one of these as a math formula. Sum of all the deviation squared, that's going to be SST. Sum of all of the predicted values minus y-bar squared, that'll be SSR. Sum of all the particular values minus our predicted square, that'll be SSE. Now, I want to be sure that we're thinking about SST, SSR, and SSE in the right way. So when we go to our next slide, SST, you can think of this as how well the actual particular values are clustered around the y-bar line. When we get to SSE, you can think of that as how well the particular values cluster around the estimated regression line. And when we go to our next slide for SSR, how to think about SSR, it's going to be a measure of how much better using y hat is for making predictions than y-bar. Again, we're going to take all those blue distances, square them, and then add them. So our relationship SST equals SSR plus SSE. And that means if we want to figure out the goodness of fit, Remember, this is the part that's explained. We simply use that in the numerator, this in the denominator. In our next slide, we get coefficient of determination, or R squared. SSR divided by SST, that is our goodness of fit, or R squared. Now, sometimes you already have SSE, the sum of the square of errors. So if you compare that part to SST and you have that percentage, you subtract it from 1. And of course, that's going to be exactly the same because SSE plus SSR make the SST. Now, R squared always is going to result in a number between 0 and 1. The closer to 1, the better the fit of the estimated equation to the XY sample data points. R squared can be thought of as the measure of goodness of fit of the estimated regression equation line to the XY sample data. You can also think of it this way: the proportion of the variability in the dependent variable y that is explained by the estimated regression equation. Now let's jump over to Excel. All right, now we want to calculate SST, SSR, SSE, and R squared. Now in this column right here, we want to calculate our predicted value using our estimated equation. So in the top cell, equals the slope we just calculated times every single one of the x values from the sample data set. And then that calculates a value for each 190 points. And then we add the intercept to each one of those. When I hit Enter, those are the predicted values. Those are all the values that would be exactly on the line. Once we have predicted values, we can compare those to the original y's. That will give us residuals. So equals all the y values. And some of those y values will be above the estimated line. Some will be below. And so when we subtract all the predicted values from the y values and hit Enter, some of those residuals will be positive and some will be negative. When you have a positive residual, that means the y value is above the line, so the line underestimates. When you have a negative residual, that means the particular y value is below the line, so the line overestimates. Now, of course, when we add all these up, Alt equals, we're going to get 0. Now we need to calculate predicted values minus the y bar. This is the distance from y bar to the estimated line. This is the explain part, or the regression part. So equals all the y hats minus the single y bar. When I hit Enter, then come down to the bottom, Alt equal, well, we're going to get 0 for that also. Now we take residual squared, so equals every single residual, caret 2, and Enter. Residual squared, Alt equals, and now we get SSE, sum of squares of the errors. Now, for all of our regression amounts, we take all of the y hats minus y bar, caret 2, Enter. Down at the bottom, Alt equals, and now we get sum of squares for regression. Now we have SST, SSE, and SSR. And for SST, here we go, equals, there it is. These are from the y deviation squared. That's the total, and Enter. SSR equal sign, and actually I have to scroll over. There's SSR, and Enter. Scroll over. SSE, there it is right there, and Enter. Now, there is not a built-in function that calculates these values directly from the x and y, at least not like slope and intercept. But there is an amazing function called sum of squares. Now, a lot of us have seen this when we try to use the sum function. We're like, what's that for? Well, guess what? For SST, all we need is the y deviations, and then this function will square and sum. Well, y deviations are just y's minus y bar. Close parentheses, and when I hit Enter, I get exactly the same thing. Now, SSR, we need all the y hats, the predicted values, and then we subtract y bar. Well, we're going to use sum of squares, and right in this argument, I'm going to create every single predicted value. Well, we take slope times all of the x values plus our y-intercept. Now, I need to subtract the y-bar, so I better put this in parentheses. And then minus y-bar, close parentheses, and sum of squares. We'll get exactly the same answer. Now, because SST equals SSR plus SSE, I can simply, because I have two of the other items, take total minus regression. And when I hit enter, I get sum of squares of residuals or error. All right, now we have all the values we need to calculate coefficient of determination, r squared. This is goodness of fit. There's all the regression. Divide by the total. And when I hit enter, I get 0.84. That's a pretty good r squared. That means that the estimated equation can explain about 84% of the total variation between the particular y and the y-bar mean. With a large r squared value like this, the equation should predict well over the experimental range. Now there's a built-in function for r squared because it's so important, and it's called smartly r square. And it takes y's, comma, and the x values. And when I hit enter, I get exactly the same, 0.84. Now there's actually another way to calculate coefficient of determination. And guess what? We call it r squared, and that's because the r, coefficient of correlation, if we square that, we get exactly coefficient of determination. And if you hover your cursor, you can see right down at the bottom, r squared is actually equal to r squared. I don't have a spot right here, but right down at the bottom, we can check this. Equals, well, there's 0.9176 correlation. And if we square it, we get r squared, or coefficient of determination. Now, another calculation we'd like to make is standard error of the estimate. That's really standard deviation of this line. That means how much variation is there between the data points and the line. Well, how do we calculate standard deviation? From Chapter 3, we take the sum of the deviations or errors squared and then divide it by degrees of freedom, which is n minus the number of population parameters estimated. In this case, we only had Xbar. Down here, we already have the sum of squares of the errors. So to calculate variance, we say, and the formula is right here, MSE equals the estimate of the variance for the regression line called mean square error. We say sum of the squares of errors, and we have to divide it by degrees of freedom, n minus the number of parameters estimated. Well, with our regression line, we estimated slope and intercept. So in this case, we subtract 2. Now this will give us the total variance. To get standard deviation of that line, or standard deviation of the error of the estimate, equals the square root, close parentheses, and bam, 52,000. That's on average the variation for each one of the data points from the estimated line. Now there is a built-in function for this, STE, straight error for y and x. And like most of the linear regression functions, it reminds you y goes first, comma, then x. And when I hit enter, I get exactly the same thing. Now we would like to test with p-value to see if it's reasonable to assume if there is a relationship between x and y. Now we're not going to go into all the details and officially use the 5 steps for hypothesis testing that we learned in Chapter 9. But we are going to calculate p-value. And the test statistic we use is the f-test statistic. Now we'll use the f-test statistics to get our p-value. And for the hypothesis test, the smaller the p-value, the stronger the evidence that there's an overall regression relationship. Now the f-test statistic, we're going to have to take 2 estimates of variance, mean square regression, mean square error. Now we already calculated mean square error right there. Mean square regression, we take sum of squares of regression, and we have to divide it by the number of independent variables. Now we have one x independent variable, So we have to divide by 1. Now we don't really have to divide by 1 in this case because we'll get the same thing, but there it is. Now we have MSE and MSR. The F test statistic, MSR divided by MSE. And when we hit enter, we get a gigantic test statistic. That is so far to the right that when we calculate our p-value, we're going to get such a small p-value that it's going to be reasonable to assume that there's a relationship. Now the F test statistics and this p-value are for an F distribution. Now we haven't studied that in this class, but nevertheless we're going to use a new function called f.dist, and we're going to use the right. The x, that's the test statistic, f, comma, degrees of freedom, that's for regression, number of independent variables, 1, comma, and degrees of freedom 2, that's for MSE. So that's n minus 2. And when we close parentheses, that p-value is so small. This is scientific notation, and that's 77 zeros in front of this number. So it is extremely reasonable to assume that there's a relationship between x and y. Now, we do want to do one other thing. We actually want to create a residual plot, and that will help us check whether the assumptions for using linear regression are met. Let's jump over to our PowerPoints. Now, this is a drawing we saw earlier in the class that describes the distribution of error values around our regression line. And one of the assumptions is that it has to have a bell-shaped distribution. And this sort of makes sense. If this is going to be a good line for predicting, then as we get further and further above or below, it's less and less likely that there'll be a value. Remember, if this is going to be a useful line for predicting, then most of the values will be clustered around this line. So the first assumption is normal distribution. The second assumption is that the expected value of epsilon, or error, has to be 0 and sits exactly on the line. And that sort of makes sense. If there's some values above and below kind of evenly distributed, then the expected value should be 0. The third assumption we're going to have to test is that the standard deviation or the variance along this line has to be consistent. Now, there's a relatively straightforward way to check all three of these assumptions. If we go to slide 79, we've talked about residuals, but this is a residual plot. Now, the way you create this is these are the residuals. Remember the difference between the particular y value and the predicted value? But we plotted this against x. And what's so important about plotting it against x is that we have our experimental region, the min and the max. And so we want to look at how the residuals behave across the experimental region. Our first assumption, the error term epsilon is normally distributed, well, that can be visually checked out if most of the dots are right along the line. That means there's a higher frequency, and then they kind of tail off on either side. Then this assumption is met. Now, it doesn't look perfect here, but there's no strong violation of this assumption. The next assumption, that the expected value of our epsilon error is 0, well, that can be visually checked out if, again, we have most of the markers right along the line, and then there's a bunch above and below. If we took the average at any particular point, it should be right on the line. And finally, our third assumption, a constant variance or standard deviation, that can be visually checked by seeing if there's a kind of an even swath all the way across from the min to the max. Now, you can see we have some spots where it kind of looks like that's not happening. There's some missing values here. But in general, there's no strong violation with this residual plot of our assumptions. So a residual plot like this, if we saw it, we'd go ahead with our inference. Now, the question, of course, comes up, what does a plot look like where we would violate these assumptions and not be able to move forward with inference? Let's go to slide 81. Now, this is straight from our textbook. This is a great picture. Now, in this case, we can clearly see the residuals start to tail off in either direction, right? They're supposed to be cluttered around the line with an even swath. That's evidence of a variance that is not consistent. This second panel here, we kind of have some residuals going up and then down. Here, the equation does not reflect a relationship between the x and y. Down here, we could see, well, wait a second. The highest frequency of dots should be right on the 0 line with some above and below. And that's not at all what's happening here. This is kind of skewed to the bottom here with some residuals tailing off. So if you see any of these, you're probably not going to move forward with any predictions or inference from our estimated equation. Now let's jump back over to Excel. Now to calculate our residual plot, we're going to need x and our residuals. I'm down at row 230 using this data set. We're going to need our predicted values. And instead of using the slope and intercept that we already calculated, I'm going to show you how to use a new function called FORECAST.LINEAR. This function will calculate the slope and y-intercept for us. And based on some x, it'll calculate the predicted value. We're trying to calculate predicted values. So we're going to put in the original x values from our sample data set. Control-Shift down arrow, Control backspace, comma. And now we have to put the y's in and then re-put the x's in, because these two arguments are what help FORECAST.LINEAR calculate slope and y-intercept. So here's the y's, Control-Shift down arrow, Control backspace, comma, x, Control-Shift down arrow, Control backspace. And now when I close parentheses and enter, there's all the predicted values. The residuals equals, well, we get our y. And I'm going to use pound to get the full spilled column, minus arrow pound. And now when I hit enter, I have residuals, positive and negative. Now I need to highlight x and the residual column, but not the other columns. So I click in the top cell, Control-Shift down arrow, Control backspace. The Shift allowed us to highlight from the top and everything in between down to the bottom. But now I need to select this without highlighting everything in between. So now I hold Control. Then I use Control-Shift down arrow, Control backspace. Now we can use Home, Analysis, Analyze Data. There it is, Insert Chart. And there's our residual plot. And sure enough, it's exactly like the one we just saw a moment ago. This will validate the assumptions, and we can use our estimated linear equation. Now, I made you do all of these calculations longhand because the math helps us understand the meaning of all the measures we created. But there's a great tool, Data Analyze Data Analysis. That can do all of these calculations with just a click of the button. Now, if you don't have that data analysis section in your ribbon, File, Options, Add-ins, Excel add-ins, go, and you can check Analysis Toolpath. All right, let's use that regression tool with x and y. Data, Analyze, Data Analysis. Scroll down, and we want Regression. Click OK. Now we're going to need our y values. So I click in the top cell, Control-Shift down arrow, Tab. And we actually have to scroll all the way back up. X values, Control-Shift down arrow. We have field names, so we're going to check labels. We're not going to create a confidence interval, but you can. And it does two of them. The default is 95. So if you change that to 99, it will do a 95 and a 99. Now we want this on a new worksheet. I'm going to call this Add Sales Reg Tool, and that will be the name of the new sheet. We want a column of residuals, and we want our residual plots. Now when I click OK, I get a new sheet, and it always comes out with the wrong column widths. So we're going to select from A over to I, and then double click between any two column headers. That best fits everything. Now here's a residual plot. We'll resize it. And there are all of the statistics. Now I made a key for you to understand all the different statistics. Let's go over to Reg Tool. Now this is your key to understanding the output. This is also slide 61 in the PowerPoints. The top number is correlation. There's R squared. There's a standard deviation for the line. Here's regression, residual, and total. There's the sum of squares. Those are the amounts we got. There's mean square regression, mean square error, or residual. Those two numbers are used to calculate f. And there's the p-value. Down here, there's the intercept and the slope. Now, to finish this video off, we're going to go look at the weight and cost data set. Here it is, BMX racing bikes. Here's the weight. Here's the price. I'm going to highlight both. Home, analysis, analyze data. And I want a scatter chart, so I'm going to insert. The only thing we need to change here is I'm going to select the horizontal axis, Control 1, and I want to change min to, and I'm just eyeing it, 19 tab. And that looks a lot better. We can see there's an indirect or negative relationship. As the weight of the racing bike increases, the price decreases. Now going up to data, we'll select data analysis, regression, click OK. Now it's incorrectly remembering the ranges from our last example. So I want to redirect them. Scroll up. Here's the y's. Tab. Here's the x values. I definitely want to change the name here, but everything else can stay the same. We'll call it weight cost reg tool. Click OK. Change the column widths. We'll move this. We can do the same thing here. 19. And this one looks OK. It's not going to cause us to reject the assumptions. So we can use the equation that we'll create from our statistics. There's R squared. The F test statistic p-value, very small. There's our intercept, and there's the slope. Wow, that was an epic video all about simple linear regression. In this video, we saw how to use the data analysis regression tool on a bike weight and cost data set and on an ad and sales data set. And then most of the time, what did we do? Did all of these calculations longhand. 12 important measures to help us create that linear regression estimated equation so we can make predictions and help us to make business decisions. All right, this is the last video for this Excel statistics class. We'll see you next class.